Property 2, the addition rule for conditional probability. Welcome, everyone. Today, we are moving on to Property 2, which is the addition rule for conditional probability. Before we dive into the new formula, let's quickly recap what we've learned so far. In our previous lessons, we established a very important concept. When we look at a conditional probability, written as the probability of event E given event F, we are essentially treating event F as our new reduced sample space. In other words, we are ignoring everything outside of F and focusing only on what happens within that specific condition. Now, here is the key takeaway for today's lesson. Because the fundamental laws of probability apply to any valid sample space, no matter how small or restricted it is, the general rules of probability that you already know, such as the addition rule, apply to conditional probability in exactly the same way. So, if you understand how to handle standard probabilities, you are already halfway to mastering conditional probabilities. Let's look at the next slide to see how this rule works in practice. Understanding the general addition rule. Now, before we dive into the conditional version of this rule, let's take a moment to refresh our memories on the standard addition rule that you already know from our earlier lessons. In standard probability, when we want to find the probability of either event A or event B occurring, we use the formula. The probability of a union B equals the probability of A, plus the probability of B, minus the probability of an intersection B. Now, you might wonder why we don't just add the two probabilities together and stop there. Well, this rule is designed to account for a very specific issue. If we simply add the probability of A and the probability of B, we end up counting the outcomes that are common to both events, that's the intersection, twice. To fix this and get the correct total, we must subtract that intersection once. As we move into the next slide to see the formal conditional statement, keep this logic in mind. When we introduce a condition, like event F, we aren't changing this fundamental logic. We are simply applying this exact same principle, but we are doing it within the restricted universe of event F. The formal statement. Now that we've revisited the logic of the general addition rule from the previous slide, let's look at the formal statement of how this applies to conditional probability. For any two events, A and B, assuming that event F has already occurred, the probability that either event A or event B, or even both, occurs is expressed as the probability of the union of A and B given F equals the probability of a given F plus the probability of B given F minus the probability of the intersection of A and B given F. To make sure we are all on the same page, let's break this formula down step by step. First, the term on the left, the probability of the union of A and B given F, represents the probability that at least one of these two events occurs, provided we are already working within the context of event F. Next, we have the probability of a given F, which is simply the probability of event occurring within our restricted sample space of F. Then, we have the probability of B given F, which is the probability of event B occurring within that same restricted space. Finally, we have the term we must subtract, the probability of the intersection of A and B. Given F, this represents the probability that both events A and B occur simultaneously, given that F has happened. We subtract this to ensure we aren't double counting that overlapping middle section. As we will see in the next slide, this subtraction becomes much simpler if the events are mutually exclusive. Special case, mutually exclusive disjoint events. Now, before we move on to our practical example, let's look at a very important special case. What happens when events are mutually exclusive? You might remember from our earlier lessons that we call two events disjoint or mutually exclusive if they simply cannot happen at the same time. Think of it like a coin flip. You can't get both heads and tails on a single toss. Mathematically, we represent this by saying the intersection of event A and event B is equal to the empty set. Because there is no overlap between them, the probability of the intersection of A and B is exactly 0. Now, here is the key connection to our current topic. If events A and B are disjoint in our original sample space, they remain disjoint even when we restrict our focus to the conditional space, F. Because there is no overlap, the probability of the intersection of A and this B, given F, also becomes 0. This is great news for our calculations because it simplifies our formula significantly. Instead of having to subtract that intersection, as we saw in the previous slide, the formula simplifies to just the probability of the union of A and B, given F, equals the probability of a given F, plus the probability of B given F. It's as simple as that. Real-world example. Imagine we are looking at a particular class of students. To keep our focus consistent with the rules we discussed in the previous slides, we aren't looking at the whole class. Instead, we are only interested in the group of students in the science stream. This group represents our condition, which we'll call event F. Within this specific group of science students, we want to look at two different interests. Some students like physics, which is our event A, and some like chemistry, which is our event B. Let's look at the data we have been given. First, the probability that a science student likes physics, which is the probability of a given F, is 0.7. Second, the probability that a science student likes chemistry, or the probability of B given F, is 0.5. Finally, we are told that the probability of a science student liking both physics and chemistry, that is, the probability of the intersection of A and B, given F, is 0.3. Our goal here is to find the probability that a randomly selected student from this science group likes either physics or chemistry. In mathematical terms, we are looking for the probability of the union of A and B, given F. To solve this, let's follow a clear step-by-step process. Step 1. Identify our known values. We have the probability of a given F as 0.7, the probability of B given F as 0.5, and the probability of the intersection of A and B, given F, as 0.3. Step 2, we apply the addition rule for conditional probability that we just studied. The formula is the probability of the union of A and B, given F, equals the probability of a given F, plus the probability of B given F, minus the probability of the intersection of A and B, given F. Step 3, now, we simply substitute our known values into that formula. This gives us 0.7 plus 0.5 minus 0.3. Step 4, finally, we perform the arithmetic. 0.7 plus 0.5 gives us 1.2, and when we subtract 0.3, we arrive at our final result of 0.9. Now that we have covered the theory and the formal formula, let's put everything we've learned into practice with a real-world example. Conclusion of real-world example. So, let's wrap up our example. Based on the calculations we just performed, we can reach a clear conclusion. There is a 0.9 or a 90% probability that a randomly selected student from the science stream likes at least one of the two subjects, either physics, chemistry, or both. This result confirms that the vast majority of our science students find interest in at least one of these core sciences. Now, before we move on to our final summary, let's quickly recap the key takeaways from today's lesson. Key takeaways. First, it is important to remember that the addition rule for conditional probability isn't a brand new concept you have to memorize from scratch. Rather, it is a direct extension of the general addition rule we discussed earlier in the lesson. The formula itself remains structurally the same. The probability of a union B, given F, equals the probability of a given F, plus the probability of B given F, minus the probability of intersection B, given F. Now, why do we include that subtraction at the end? As we saw in our earlier slides, subtracting the probability of the intersection, which is an intersection B given F, is absolutely necessary to avoid the mistake of double counting the outcomes that belong to both events. Finally, keep in mind the special case we covered regarding mutually exclusive events. If the events are disjoint, the intersection is simply 0, which means the formula simplifies beautifully, and you can just add the two conditional probabilities together. All right, let's wrap up what we've learned today by reviewing the key takeaways. In our next session, we will look at some common pitfalls to avoid when applying these formulas in more complex problems. Common mistakes. First, watch out for forgetting the intersection. A very frequent error is to simply add the probability of a given f to the probability of b given f, without checking if the events are disjoint. Remember what we discussed in slide 4 regarding mutually exclusive events. Before you finish your calculation, always ask yourself, can A and B happen at the same time? If they can, you must subtract the probability of the intersection of A and B, given f, to avoid double counting. Second, be careful with your notation. It is easy to get confused between the probability of the union of A and B, given f, and other similar-looking expressions. While the notation might look slightly different at a glance, always remember that the condition f applies to the entire union of A and B. Keep your brackets clear so you know exactly which part of the event is being restricted by the condition. Finally, a crucial point: ensure you are applying the general rule consistently to conditional probabilities. Do not mix and match. You must use conditional probabilities, such as the probability of a given f, throughout the entire equation. A common mistake is to accidentally use standard probabilities, like the probability of A, instead of their conditional counterparts. To get the correct result, every term in your formula must be operating within that same restricted universe of f that we established at the beginning of this lesson. Now, as we wrap up our lesson, I want to highlight a few common pitfalls. Even if you understand the logic we've discussed today, it is very easy to make these mistakes during an exam. If you can avoid these 3 traps, you will have a much stronger grasp of the addition rule for conditional probability.